Hey, Dr. G here. As promised, I'm going to go ahead and make a video for you to watch that will kind of walk you through the mechanism of DNA ligase. You're told that the reaction starts with the side chain of lysine and its reaction with ATP. Okay, so I'm going to abbreviate ATP. Each of these P circles represent a phosphate group, and then we have our alpha phosphate here that is a little more relevant. Okay, and I'll go ahead and draw the structure of ATP just once here, but then I'll abbreviate it moving forward. Okay, so here's our ATP. In this step, what happens is that this nitrogen makes a covalent linkage with that phosphorus, with the alpha phosphorus, and we release pyrophosphate or diphosphate, okay? That hydrolysis of ATP to pyrophosphate and AMP is the energy that ultimately is the driving force for this reaction. And as we've talked about over and over, we must capture that energy in the form of a covalent bond, okay? So that covalent bond that captures the energy is the bond that I'm showing formed right now between the nitrogen and this phosphorus. Okay, the electrons flow up onto that oxygen, creating an oxyanion pentahedral intermediate around the phosphorus, which collapses, and we release pyrophosphate. Okay, so pyrophosphate is one of our products, and we've now created a covalent linkage between lysine and AMP. Okay, and this A here represents the rest of AMP. Okay, the important bond here is this one right here. That's the high energy bond that traps the energy of ATP hydrolysis. Okay, also note here that I drew lysine in a way where it was deprotonated. Remember, inherently there are general acids, general bases around, so we don't have to show every single protonation, deprotonation step. I'm comfortable with you assuming that they're there, okay? If you need to draw them out for your own sake, like for your own mental health, do it. But as biochemists, we can confidently assume that they're there unless they're absolutely critical in the reaction. Then we show them, okay? So this is our first intermediate. In the next step, we are told that the 5' phosphate of the growing or the existing DNA chain serves as a nucleophile and ultimately creates a diphosphate linkage between the 5' end of DNA and AMP. Okay? The only way for this to happen is for one of these two oxygens to be a nucleophile. Okay? Not expected, but possible because enzyme active sites can do cool things. So choose one of the oxygens, make it a nucleophile, make a bond between the oxygen and that phosphorus. We form our intermediate, which collapses, and in this case, we're gonna need a general acid here. This bond between the phosphorus and the nitrogen is broken, and we end up releasing lysine, right? So the lysine side chain is reformed. So back to where we started there. And we now have a covalent linkage between the 5' end of our DNA and AMP. So here, the A is the rest of AMP. Okay, so this is our second high energy bond. So this phosphodiester linkage is our second high energy bond. The diphosphate is not especially stable. So we can certainly imagine hydrolyzing that bond, releasing AMP, would be a favorable process that could help drive forward something else. Okay, and in fact, that something else, we're told, is the 3' end of our DNA chain coming in. And I'll move it down here a little bit. All right, so the 3' end of our DNA coming in and covalently being linked up with the 5' end. So we're going to need to have a general base in the active site of the enzyme that activates this to be a good nucleophile. So electrons flow up to oxygen. We have an oxyanion that's now an excellent nucleophile that can attack at the alpha phosphorus of the 5' end of the DNA, not the phosphorus of AMP. Electrons flow up to make an intermediate, recollapse, and then the bond between the diphosphate linkage is broken. We release AMP, right? Here's our AMP that gets released. That's our leaving group, and that's one of our products. And we have also created now the phosphodiester bond that needs to reform in our DNA. So here's the 3' end, the original 3' end, being now linked up with the original 5' end. So our DNA chain has been resealed. That nick has been fixed. Okay? So the mechanism is not one that you would just inherently know. But given information about each step, it's something that you should be able to think through. Lysine in the active site creates an initial intermediate with AMP. Okay? So given that information, you should be able to predict this reaction. We then see the phosphoamidite linkage broken, and it's replaced with a diphosphate linkage with the 5' end of DNA. So AMP is linked to the 5' end of DNA through this diphosphate linkage. That's the second step. The third step, the 3' hydroxyl comes in and replaces AMP. Okay, each step involves translating that energy of the original ATP hydrolysis. And that's what I really want to stress in this mechanism, is that ATP hydrolysis doesn't magically power this non-spontaneous reaction. Instead, it's translated through covalent bonds. And the covalent bonds are high energy and reactive, which makes subsequent steps possible. All right, as always, if you have questions, come ask me.